Welcome to module 35 of database management systems. We have been discussing about concurrency control. This is the second and concluding module on that. So, in the last module we have talked about the basic issues in concurrency control and particularly talked about lock based protocol and how to implement locking in very simple terms. As we have seen that deadlocks are the perils of locking. I mean we cannot do without locking and certainly if we lock, then deadlocks are inevitable almost to happen. So, here first we try to understand how, since deadlocks are inevitable, so there has to be mechanisms to detect deadlocks and recover from them. And also we would like to look at if it is possible to create strategies which can prevent deadlock from happening at all. And so, after having studied that, we would like to understand, take a look into a simple time based protocol that can avoid deadlock. So, deadlock handling. So, system is deadlock if there is again just to recap, the simple idea is if there is a set of instructions such that every transaction in the set is waiting for another transaction in the set, and therefore, none of them can actually proceed. So, deadlock prevention protocol ensures that the system will never enter into the deadlock state. So, the question is, can we make some strategy? So, why are we getting into the deadlock? Because transactions are making requests for different locks and those are granted, and then some more requests come and we come to a state where A is waiting for B, B is waiting for C, C is waiting for A kind of a situation, and we get into the deadlock. So, can we have strategies so that the requests and releases are done in a way so that the deadlock will not happen at all. So, fortunately such number of such strategies exist. For example, one strategy which is called the pre-declaration, which require that each transaction locks all data items before it begins its execution. That can be shown that that ensures that you will never have deadlock, because but in very simple terms, you will not be able to start before you have got all the locks, and once you have got all the locks, naturally you have every access to all possible data items, and therefore, you will be able to proceed. Naturally, the flip side of this is this will delay the beginning of the transactions to a great extent in many cases, and particularly will bring down the level of concurrency that you can have. The other, which is smarter, is what it does is imposes a kind of partial ordering of all the data items that a transaction, all the data items that exist, and it requires that a transaction can lock the items in only in that specific order. So, the important thing here is a partial order among the data items, and the fact that you lock data items in that order that is specified by the partial order. You cannot lock out of order, and if you can do that, then it can be shown that the deadlock will get prevented. We cannot, we do not have time to go into the details of how that works, but I just want you to know that such strategies of prevention exist. So, the other possible prevention schemes that we would like to look at in little bit more depth is the fact that I can use timestamps for the transaction and use those timestamps, that is, which will tell me which is an earlier transaction and which is a later transaction, for preventing deadlock, and several strategies for that exist. We will discuss two of them. First is what is known as wait and die scheme, which is non-preemptive. Non-preemptive means that in this no one preempts anyone else. So, what do you do in wait and die? The older transactions, because you assume that every transaction has a timestamp. So, smaller the timestamp, older is the transaction. So, older transaction may wait for the younger one to release the item. So, if two transactions are conflicting, then the older one will wait, and the younger transaction will never wait for the older one, they are rolled back instead. So, if there is a conflict, then the younger one in that will always roll back and the older one will wait. So, a transaction may die several times before acquiring the needed data item. kind of starvations may happen, but certainly there will not be a deadlock, because A waiting on B and B waiting on A cannot happen, because out of A and B one must be older, has to be older, and that only we will wait, the other one will abort and roll back. The other is a preemptive scheme, which is called wound and wait scheme, where the older transaction owns up or forces a rollback of the younger transaction instead of waiting for it. That is why this is preemptive. So, the older transaction is preempting the younger transaction to continue to wait, and forces it to roll back to abort, and but the younger transaction may wait for the older one. So, by doing this preemptive one also, it is possible to have a fewer rollbacks than the other scheme. So, it is a preemptive scheme, but the advantage is it might allow you fewer rollbacks to happen, and with these two kind of timestamp based schemes, it is possible to actually prevent deadlocks, and for that reason these kind of schemes are often preferred in many contexts. So, both in wait and die and wound and wait scheme, the rollback transaction is restarted with its original timestamp. This is a very important point to note. When you restart, so you have rolled back, so you have to restart that transaction. Now, when you restart the transaction, you do not put the timestamp of when it is being restarted. You put the timestamp of its original time, the time when it was started and had to be aborted and rolled back. So, the older transactions have precedence over the newer ones, and that starvation will get avoided. So, now what becomes, you are actually a new candidate, because you had been rolled back and started again, but you carry your older timestamp. So, your precedence has gone higher, because in wait and die and wound and wait, in both actually the older one has a precedence. So, by carrying your older timestamp, you inherently bring in a higher precedence in the system, and in this way there is a precedence based ordering that will naturally always happen. So, this will not only avoid deadlock, but this will also ensure that starvation is avoided. So, very simple and nice scheme. So, in this you usually have timeout based scheme. A transaction waits for a lock only for a specified amount of time. If the lock has not been granted within that time, the transaction is rolled back and restarted, and therefore, the deadlock is not possible. It's simple to implement, but starvation can happen in the timeout based scheme. And it is also difficult to determine what is a good time interval to wait. If you wait too short, then you will spend a lot of time in the rollback and restart. If you wait for too long, then your throughput will go down, because several transactions are basically waiting on locks. So, theoretically it does avoid deadlock, but in terms of starvation and in terms of the practicality, there are critical things to decide on this. The second issue in terms of deadlock that we must be able to answer is, well, hundreds of transactions are going on in the system. Now, how do you know that a deadlock has happened? Because if a deadlock has happened, and if you are not using a preventive scheme to ensure that the deadlock will never happen, theoretical proof, if you are allowing, say, two phase locking kind of protocol where deadlocks can happen, then you must know what must be able to detect that a deadlock has happened, and then take care of it to roll back the transaction. So, for doing this, we again create a graph which is wait for graph, which is very similar to the precedence graph we saw earlier, which the nodes are the transactions and the edges are ordered pair of transactions. So, what you put an edge from T I to T j, you put this edge in what it means is T I is waiting for T j. So, if we have a conflict, then certainly one transaction is holding the lock and other has requested for that lock. So, what you do, you put an edge from the one that is waiting for the lock to the one that is already holding the lock for the release of the lock, and in this way the graph gets built up. So, naturally when T I requests a data item currently being held by T j, then the edge T I T j is inserted in this graph, and when the release happens, then this edge is removed, because T j is no more holding the item that T I had actually required. So, this is how this is kind of a dynamic graph. The wait for graph is a kind of dynamic graph which will regularly keep getting updated. Now, naturally from the description of this graph you can understand that a deadlock, if a deadlock has to happen, then this graph must have a cycle. So, if at any instant the graph has a cycle, then there is a deadlock. Otherwise, the graph will grow and shrink, it will keep on happening that way. So, it is important to ensure that this graph remains acyclic, which now this is dynamically happening. Hundreds of transactions are getting created, they are getting committed, aborted, they are requesting locks, they are releasing locks and so on. So, how do you ensure that the graph at every stage is remaining acyclic, or a cycle has happened and therefore, a deadlock is actually happening? So, what you will need to do is periodically run another process which invokes the deadlock detection in the graph, that is, it looks for the cycles, and if the cycle is there, then you have to do some strategy to roll back abort one of the transactions and break the cycle, and then so that the other transaction can proceed. So, these are examples of the wait for graph. For example, here on the left, as you see, if I may point out, in the left, if you see that T 17 is waiting for T 18 and T 19, T 18 is waiting for T 20. So, eventually, and T 20 is waiting for none. So, at some point of time T 20 will be done, and when that is done, then T 18 would be able to proceed, and if T 18 is able to proceed, then T 19 would be able to proceed, and then T 17 would be able to proceed. So, there is no possibility of a deadlock, whereas in here, if you look in the graph on right, then you can see that between these three they are waiting on each other. So, no matter how long you wait, this deadlock will never be broken, and the deadlock detection system has to detect this cycle and decide to abort one of these transactions, and so that the rest of the transactions can progress. So, this is a simple deadlock detection mechanism. So, when the deadlock is detected, there has to be a recovery. So, transactions will have to be rolled back to break the deadlock, and so there is a strategy required to select which transaction must roll back. Naturally, that should be done based on the minimum cost. That is, you do not want, because if you roll back, then there is a recomputation naturally, because you have to restart and do that transaction again. So, you have to, in terms of rollback, you have to determine how far to roll back that transaction. That can be a total one, so that you roll back the whole transaction abort and then restart it, or you can roll back to a previous point. We discussed notions of save point in the transaction program, and so it is be more effective to roll back transaction only as far as necessary to break the deadlock. You may not need to roll back everything. Maybe this transaction is participating in the deadlock because it is holding some exclusive lock which it took 3 instructions before, but before that it has done 300 instructions. It is not necessary to roll back the whole of the 300 instructions. You can just roll back up to the point where it took that exclusive lock which is creating the problem. So, those are some of the strategies which can improve the throughput and minimize the possibility of starvation. Starvation will again happen if the same transaction is chosen as a victim to be rolled back every time, which the possibility exists. And so, the number of rollbacks is also usually kept as a cost factor. So, when you roll back a transaction, you also keep a number saying that how many times this transaction has been rolled back. So, higher that cost becomes, then you would like to avoid doing the rollback for that transaction, because so that it does not wait infinitely in terms of a starvation. So, these are some of the simple strategies that rollback the deadlock recovery can be done. So, having talked about the prevention, detection and recovery from deadlocks, let us quickly look at a simple time based protocol in contrast to the 2-phase locking protocol we had earlier. this protocol does not lead to deadlock. So, what you do in here is each transaction is issued a timestamp when it enters the system. So, older the transaction, less is the value of the timestamp. So, that is a simple. So, time goes in the increasing order. Now, the protocol manages concurrent execution such that timestamps determine, they themselves will determine the serializability order. They will determine in which order the transactions should occur. And for that, for each data item, two timestamp values are maintained. One is the write timestamp on the data item q, another is the read timestamp. So, this is the latest read, write and read times for the data item. So, w timestamp q is the largest timestamp of any transaction that executed a write q successfully. So, naturally what it means? The largest timestamp means the latest write that has happened. Similarly, it gives the latest read. Now, using that you build up this protocol. So, it is again looks only at conflicting read and write operations, and they are executed in timestamp order. So, let us suppose that let us consider the case of read. So, a transaction T I has issued a read. Now, if that the timestamp of T I is less than equal to w timestamp q, which means that w timestamp q is the latest write and T S T I is the timestamp of the transaction. So, the transaction is older than the latest write. So, the transaction T I needs to read a value that was already overridden, because the latest write has happened after the transaction. So, this read operation can be rejected and T I will be rolled back. If it is in contrast, if the timestamp of the transaction is greater than the latest write time w timestamp q, then the read operation is executed, and since we are doing a read operation, so this becomes the latest read operation, and therefore, the read timestamp r timestamp q is set to the maximum of the current read timestamp and the timestamp of the transaction. Mind you, here the timestamp, one confusion that may come to your mind is, are we looking at the exact time when the read has happened or when the write has happened? No, we are, all of this reasoning is happening with the timestamp of the transaction. So, whenever it had started. So, it is an older transaction and newer transaction that you are reasoning with. So, when you update r timestamp, then your the r timestamp already has a value which is the timestamp of the latest transaction that has read that value, and T S T I is the timestamp of the transaction that is read it now. So, it is not always that since this read is the last read, you will update this. So, by the sense of latest, what I mean is the latest in the sense of the timestamp of the transaction that is reading it. So, you will compute that in terms of finding the maximum of the current read timestamp and the timestamp of this transaction. Write is little bit more complex, but we can reason in the same way. So, if T I issues a write q and if the timestamp of T I is less than r timestamp, that is, if this transaction is less. So, it is older than the read timestamp, that is, it is older than the transaction that read q last, the youngest transaction that read the value of q. So, then the value q that T I is producing was needed earlier. It is trying to write, but already a newer transaction has used the value, and the system assumed that what the T I was supposed to write was not available, was not produced. Hence, the write operation is rejected. T I does not, should not write this, and T I will be rolled back. Second case, if the transaction T I has a timestamp which is less than the write timestamp. So, which means that this transaction is older than the transaction that has done the last write. So, Ti is attempting to write an obsolete value of q, and hence this write operation is again rejected and Ti is rolled back. Otherwise, in other cases, the write operation is executed and the write timestamp will be set to the timestamp of this transaction which has written it. So, this is a very simple protocol for read and write, and here is an example shown in terms of this protocol. For example, this wanted to do a read and this. So, this is the time where the transaction had started. So, and this was the write that. So, when this read is happening, this is the. So, this is naturally this is an older transaction than T3. So, this at this point the write timestamp is that of T3 and this is an older one. So, it was trying to read that. So, this was aborted. Similarly, as you see here, if I clean and start again, if you look at write W, this is trying to do read and T4. So, read will this read has a timestamp which is of T4, which is later than the timestamp of T3. So, this gets aborted. So, you will need to spend a little bit of time to convince yourself that this will never actually ensure never actually lead to any deadlock, and is a very effective serializable and simple strategy to ensure serializability while it avoids the deadlock at all. The timestamp ordering protocol itself guarantees the serializability. So, the transaction with a smaller timestamp will lead to transaction with larger timestamp, because those are the more recent transaction. So, since the ordering is always in this manner, there cannot be any cycle in this precedence graph, because if there were a cycle, then naturally somewhere you will be coming from a newer to an older transaction, which is not allowed in this protocol. So, there cannot be a cycle, and so this ensures that there cannot be deadlock in this time based protocol, but the schedules that they produce, they may not be cascade free, and actually examples can be shown that they may not even be recoverable. There may be some irrecoverable schedules that get produced through this time based protocol. So, to summarize, we have tried to take a look into explaining what are the different ways to prevent deadlock, some of the strategies, and specifically we focused on the time based strategy. So, there are some strategies which are based on the order of accesses, the data items, ordering of data items and so on, and we have specifically focused on time based strategies and shown that there are multiple time based strategies which can prevent deadlock. And in case deadlock has happened, then we have discussed a simple wait for graph data structure and algorithm to be able to detect that the deadlock has happened. And if once this has been detected, we have talked about basic strategy to recover from that. That is, how do you decide what is a good candidate victim transaction which should be rolled back, which should be aborted. And on that study, we have presented a simple time based protocol which maintains the timestamp of transactions to decide the ordering in terms of read and write, and deciding as to whether you should continue doing a read or write, or you should abort the read and write attempt, and thereby ensuring that deadlocks do not happen in the system, though there may be other problems in this, in terms of having cascading rollback or having some irrecoverable schedules at times.